the key problem that we had here was that we had to design these gray control boxes, which controls, for example, you remember that in the LOA and LOB, they control the inputs to the arithmetic logic unit. And depending on the type of the instruction, then the different values should be forwarded to it. So it's like a multiplexer, in which we multiplex the proper data at the well, at the proper context. And so we started designing this, and I will now let it go fast forward to this. I'll just give you some examples in here. So in this case, we have this arithmetic logic unit here, and we have this LOA block, LOB block, then we have the set CC and the LO function. So these are the blocks that we should design. The ones in blue, they're already designed. So if I tell you, to design arithmetic logic, you can do this with your logic design, background, okay? Or when I talk about, CC, then it's pretty easy. It's like just three registers, right? And then I have, for example, this condition, basically the signal generator, which is, it takes two things. It takes the IFUN, like, and remember the condition signal, it checks whether the condition for a conditional instruction is satisfied or not, which happens in a conditional move case or a conditional jump. In that case, you look at the IFUN, which tells you the condition, and then you also then look at the CC values. And with these two, then you can generate this one-bit number, which is called the condition, which tells you whether it's satisfied or not. So in here, we looked at, what we should be, for example, doing this LOA. All the design, by the way, the design for all this sequential processor. Remember, we are designing this in HCL, and this is essentially available as a full HCL code, which is part of the book, and you can also download it. And in your third assignment, you will actually be working with this HCL code to append new instruction to the instruction set. So what we did was, remember when we were looking at, for example, the LOA input, which was this one. So I'm talking about this design. And all we had to do is, we go through for all the instructions. And in this particular case, I only have a subset of them, which are basically key, but you should assume that, I take all the instruction and I look at their execute stage. Okay, what is the computation that I should be doing? And with this, then I can look at what's the input that I should be feeding. So, for example, if I'm working on a arithmetic logic instruction, then it's always value A, which is what you read. Remember, this is what we would read from register RA, right? Or in this case, condition move, again, val A. But if it's, for example, register to memory move, then we define this as a value C. If it's a pop, then it's a +8. If it's a call, it's a -8, and so on. So with this, then I can define this LOA. Remember, what I'm doing is, this is my LO, and I am designing this circuit, which is basically, this is the signal that I'm generating. This is LOA. This is the signal that I'm generating, and this is the function that's defining this code. And what's saying is, we said it's the I code, so it takes an input as I code. If it's register to register move or arithmetic logic instruction, then it should be value A. So I also take value A here, which is a 64-bit number. And if it's immediate to register move or register to memory move or memory to register move, then it should be value C. So I also feed value C here. Or if it's I call or I push, it should be -8, which you define this as a 2's complement number. Or if it's return or pop, it should be +8. So you also feed or +8 here or -8 here. And depending on I code, then you forward one of them to the A input of LOA. Okay. So this is basically how we design this whole thing. The key thing is the design these control boxes. And that's it. And it's essentially writing codes like this, which actually defines how the processor works. So there are all the other things like a allo operation. Remember, the allo operation is basically defined by this. you can see that in my discussion, like, in this case, there's something like called set CC control block or like something else. And then for all these all these control blocks that are also defined, and but they are not covered in the slides. Instead, if you look at the HCL code for the sequential processing, then you should see and understand basically that it's actually there. So, and this is the part where, for example, where we work on the data memory part. Okay, again, let's just go here. It's like, here's my data memory. So this is a memory where we need an address, a data. Okay, if you're going to write something, a write signal, then remember this is a 1-bit signal, a read signal, again a 1-bit signal. And then the question is, how do we define, how do we set these control boxes? Again, for this, again, all you have to do is, for example, I want to compute the memory address, and I look at the memory stages, the computation of the memory stages of all the instructions in my ISA, and then you look at, what I should be feeding as the address. These are the addresses, right? And based this, then I can say the mem address. If the I code is one of these instructions, then it should be output val E. If it's pop or return, it should be val A. Okay, that's it. So in this case, this is my data memory, and then I need to feed the address here, okay, which is 64 bits, and I have this control box. And in this control box, then I should remember this control box is essentially the combination circuit. I have an I code, which is important, and then val A, and val E. Note that these values, val A and val E, these are all signals that were generated by the previous phases. Okay, so you can only use the signals that are computed before this current stage. And the last stage that we did was the PC update stage. And well, this is kind of like, it's like magical, right? What this does, it tends to compute a new PC. And for this, you can say that it looks at the I code. And then it uses the condition. Remember, this was a 1-bit number, which tells whether the condition is satisfied for conditional move and conditional jump instructions. It's important. And it takes val C, val M, and val P. And based on this, then it generates this new 64-bit address for of the next instruction. So what we do is, again, we look at the PC update stage. For example, if it's an arithmetic logic instruction, then we update PC with val P. Remember what val P was, it's the address of the next instruction in the flow. And if it's, for example, just the memory move, again, it's val P. If it's a pop, okay, then it's again a val P. If it's a conditional jump, then PC is slightly, it depends on the condition. If the condition is satisfied, then you jump the val C. This is your target. Else, you basically fall through. You basically move to the next instruction. In the case of a call instruction, then it's val C, because the destination that you call, this is val C, is the address of the first line of the function that you're calling, so it's val C. And if it's a return, then it's val M, because this is the return address, right? So this new PC, which is, so we have this register PC, and before this, and we have this box here, which says new PC. Then it says it computes the new PC and then feeds into this PC, where this is, remember, it's a register. Because this one is a combination circuit. So don't confuse, they are completely different things. So the register has a state, whereas the combination circuit doesn't. So in this case, if the I code is a call function, then it should return val C. If it's a conditional jump and the condition is true, then it's val C. If it's returned, then it should be val M. And for there's the default, then it should be val P.